Greetings, CHEM1412 class. What I want to do now is just take a lightning speed look at the material that you should have covered so far. And I'm going to do that by way of going over some old face-to-face lecture notes and just giving you my thoughts. Again, I'm going to try to cover everything in a month's worth of chemistry in about 10 minutes. So here we go. Chapter 20, Organic Chemistry. There's a couple of essence topics that you need to know. Essentially, what you're supposed to do here is to be able to name some basic compounds. So to do that, you need to remember the basic rule of you find the longest branch and you start numbering it from the functional group. And so there's a couple of examples here. Now, the other thing is you have functional groups. Everything is not an alkane. Everything is not an alkene. Everything's not an alcohol. So you need to know what those are. If you look at one of the tables in the books, you will see that it gives you all of the functional groups. So the two key things you need to know out of chapter 20 and be sure you can do is, one, you understand what the functional groups are so you know whether to name it as an alcohol, an alkene, an alkane, an alkyne, an aldehyde, or a ketone, or an acid, or an amide. You need to know what the functional groups are, and then you need to know how to pick the longest chain out and pick the end that you start. And the end is the end that you start with. The end that you start numbering is typically defined by some rule that will be based on a functional group. That's what I see as you needing to know out of chapter 20 on nomenclature. Chapter 10, solids, liquids, IMFs, intermolecular forces. This is the whole punchline of chapter 10. There's some basic fundamental forces that hold everything together, that allow it to interact. And so here's the punchline. And if you look at what I've got shown here with my cursor, you've got intermolecular forces pulling atoms apart, and you've got kinetic energy, motion, pushing them apart. And that's the world of chemistry. That's it. Something's trying to pull it together and something's trying to push it apart. So who wins and how much? Okay, so one of the things you need, and it's going to talk about the four basic types of interactions. And one of those is called dispersion interactions, which you'll learn about, and one of them is called polar interactions. There's explanation of dispersion interactions. That gets me to this point. Now, why are we teaching you about these four? Because it's from these four that you understand chemical properties. For example, arrange the hydrocarbons in increasing boiling point. Okay, well, you can think about the four types of forces that are in play, and then that will allow you to predict. So the whole punchline of these four, teaching you these four forces, is that you can do two things in the future. One, you can predict physical properties, and two, you can possibly predict reaction properties. That's the whole idea. It's not there just to give you something to memorize. And well, that's part of it, just to have you something to test on. But this is basically it. Okay. So then everything from, and there's all sorts of stuff in the text. So how does a gecko work and all of that stuff? It all comes down to these interactions. Okay, so we talked about dispersion interactions, then there's polar interactions, so-called dipole-dipole interactions. That's where everything acts like a magnet. And then there's a special type of dipole-dipole called hydrogen bonding. You need to recognize those. Those are a big deal. There's the relative strengths right there. Dispersion is less than polar, is less than hydrogen bonding, is less than ion. There's your four right there. This relative strength, that little box right there, is the punchline of this. And the rest of this chapter is taking these four types of forces and predicting things like what? Boiling point, melting point, viscosity, surface tension, understanding why wax beads water. Okay, so there's one, match the viscosity. So you look at these properties, you look at the structure, you see which forces are in play, and you predict. That's it. Everything. It explains capillary motion. It explains a whole lot. Here's a long question that has to do, oh, by the way, with how much something rises and falls in a capillary tube. Don't worry about that. Why I put this on there is that I wanted you to see what a very good dimensional analysis set up, how it can help you solve a very difficult problem, as far as there being a lot of things that you have to keep track of. Okay, so there we are. Here's another. Arrange in order of increasing melting point. There we go. 4 compounds. You're supposed to recall those are your 4. And you rationalize the answer based on what you know of those 4. That's it. Okay. Another thing you can rationalize using those is phase transitions. We all memorized in Gen Chem 1 there were 6 phase transitions. Now you can understand that better if you understand what the interactions are in between each of those molecules that you're trying to melt or freeze or vaporize or whatever. Okay. One of the key factors that you can look at is vapor pressure. That's just another one of the properties. Why that vapor pressure is particularly important is you're going to have this thing called colligative properties after a while. And because properties affect vapor pressure affects colligative properties. And that's how that fits in. Remember I told you that it was kinetic energy forcing things apart, and then these 4 forces pulling them together. That's why the textbook then goes and talks about kinetic energy. It's trying to get you to understand the other piece of the equation. There we go, boiling points and vapor pressure. So it's tying it all together. Boiling points are related to vapor pressure, and vapor pressure is related to, you got it, those same 4 properties. Okay, let's see. Mathematical relationship, what you're going to see a lot of is boiling point, temperature, and pressure. See, there's 3 physical properties that you need to look at. So I kind of saw a little pattern here. And this is called the Clausius-Clapeyron equation. And basically, it comes from the Uranus equation. You're going to see that over and over and over and over in science. If you haven't already, remember it takes this form. I've rearranged them. That's what my little loop means into these. You can ratio them and get something that looks like this. Okay, pardon that interruption. There we go, normal boiling point. Okay, enough on that. So you now get the punchline. There's 4 properties, and that they are working to pull molecules and atoms together, and then you've got kinetic energy trying to force them apart. And that give and take between those is how you rationalize physical and chemical properties. Boom. And then there's a bunch of memory stuff, and then we get talking about thermodynamics and heat a little bit. Okay, heat is one of those properties that affects how tightly or how loosely something's held together. And then it goes on to tell you how to predict how to do some Q equal ms delta T calculations. Okay. By the way, the punchline on those are as you go laterally on this graph, there is no delta T, so you're going to use a different formula. You're going to use the Q equal M delta H for a phase change. Yes? And then when you have a change in temperature, you're going to use the Q equal ms delta T. So that's one indication of when to use which one of these equations you're going to use. Use one of these when there's a temperature change, and use another one when it's a phase change. Okay, there we go. You can look back in some notes that I posted. A lot of these problems that are worked out, they're not going to be shielded here. The purpose of this is just to give you a flyover, not to actually work the problem. So let's keep moving on. 10 phase diagrams. Okay, so kind of learn about the phase diagrams, and that's basically where you can see the conditions which produce solid, liquids, and gases. A couple I would note would be the triple point. That's where something exists as all 3 at the same time. Yep, that can happen at one very specific point called the triple point. And there's also a thing called the critical point, above which it's just kind of an amorphous in between a liquid and a gas. You can't really tell what it is. Okay, so there we go. Let's see. Couple things I wanted to know. This mole. Molar mass converts gram to moles. You can convert liters of solution to moles by molarity. You can put kilograms to moles by molality. You can use the ideal gas law. And the punchline is all roads lead to Rome. Almost all chemical calculations lead through the mole. So notice many formulas are given have a mole term in it. So that's one thing you need to realize. Let's see what I want to do. Let's go to really quick to chapter 11. There's this thing called the dissolution process, which I don't have the diagram on this, but it basically is this. It's trying to get you to understand the process by which something dissolves. It's a little more complicated than you might think. So if you know a solution is a solute plus a solvent, here's what you got to do. To dissolve something, you got to pull the solvent molecules apart and make a pocket. you got to pull the solute molecules apart because they're sticking with each other, and you put one solute molecule down in the solvent pocket, and then those interact. And so it's a sum of all of those interactions, and you wind up getting something, oh, I don't think I can zoom that up, that looks like this, where you're breaking the solute molecules apart, you're breaking the solvent molecules apart, and then you're mixing the solute with the solvent. So some of these take energy and some of them give off energy. The punchline is, if you get off more energy than you put in, it's going to happen naturally. The ball's going to roll downhill. If you have to add a lot more energy than you get back, then that's kind of uphill, and it ain't going to happen spontaneously. Spontaneous, what say you? That's something that occurs naturally, okay, that you don't have to put energy into it. Let's see what else. It talks about entropy, study and gain. Okay, that's pretty straightforward. Electrolytes. Now we're getting into talking about a specific type of interaction. Before, the ion actions, when you have things that are ionic, they attract each other. And so when you have something called electrolytes, like Gatorade or whatever, the molecules come apart into ions that attract each other. Okay, so now what this electrolytes is doing is it's drilling down on that fourth type of intermolecular force you learned about earlier, ion. See, it's all kind of tied together here. Solubility, you're learning about one thing being soluble in another. In intro chem, it's a cheat. I either have people memorize, it's either soluble or it's not, but guess what? There's degrees of solubility. There's a solubility spectrum. And also, you can get something that's beyond saturated. Okay, you can actually do that if you can get the entropy working just right. All right. Solutions of gases. So what's a solution? A mixture of one thing and another that does it homogeneous. So realize you can have a liquid dissolved in a liquid. You can have a gas dissolved in a liquid. You know, you can have any version of this. Okay, so here's a section that talks about a solution made of a gas and a liquid. All right, so that's basically where you dissolve carbon dioxide or something. That's how colas work, right? You've got, that's what fizzes out, carbon dioxide. You've got a gas that's dissolved in the liquid. That's how come fish can breathe. How do they breathe? Well, they kind of do it through their gills. Well, what are they breathing? Well, oxygen like you and me. They don't have lungs. They've got gills that pull oxygen out. Well, I thought oxygen was a gas. Well, it is a gas, but there's a little bit of gas dissolved in liquid. There's a little bit of oxygen dissolved in water. And that's what the fish live on. Henry's law, very important relationship, and the first time you will see the concentration of a gas is equal to some constant times the pressure of the gas. What is significant about this is the concentration of the gas we're talking about in the liquid phase, and the pressure of the gas we're talking about above the liquid. So this is one of the first equations where you have a single relationship that talks about gases in different phases. Before, you had like the total pressure was equal to the pressure of all the gases, but in the gas phase. So all of those gases were in the gas phase. You've got equations where it relates to concentration of all of the liquids that are in the liquid phase, but this one has a component for something that's in the liquid and above the liquid. So Henry kind of did that. So you'll see Henry's law. It's pretty easy peasy to understand. I mean, come on, it's something equals something times something. That's not too tough for a STEM major, hopefully. How do the bends work? Just right quickly. See, there's a concentration and a pressure. And so if you're way down beneath the ocean and you come up really fast, guess what happens? The pressure decreases very quickly. And so what happens is the concentration in the liquid decreases. And so when the concentration decreases, it releases it as a gas. And you get all these gas bubbles in your blood. And that, they tell me, is a really bad thing to happen. Okay? It's really painful if it's not lethal. Okay? So you don't want your blood to start. It makes my blood boil. You don't want your blood to boil. You don't want your blood to boil. And Henry's law will tell you about that. Okay, and there's some practice problems with that. You can have solutions of solids and liquids. Yeah, you can have anything and anything. Okay, colligative properties. So this is one that's based on vapor pressure, which was, of course, based on a balance of those four. And a colligative property is basically a property that's a function of the amount of material, not the kind. And there's four colligative properties: vapor pressure lowering, boiling point elevation, freezing point lowering, and osmotic pressure. And so when you read the book, you'll see that there's a whole lot of problems working with those, and you need to know how to do those. Punchline is you really are going to need three main variables. You better know what molarity is, but even more than that, you better know what molality is. It's the concentration based on not the liters of material there, but the kilograms of solvent. Okay? Right. Most of the colligative properties are written in terms, concentration terms of molality, not molarity. Okay, there's some sample problems. You can kind of review those. Basically, why these work is it lowers the vapor pressure, and once the vapor pressure is lower, that's what really affects these other three. So essentially, we say there's four colligative properties, but these three are essentially caused by this one. Okay, that's the root cause. Dalton's law of partial pressure. Again, you've got equations which relate the pressure of something. Partial, what does it mean partial? Well, if you've got two things in a gas phase, then two gases, then both of them are pushing against the walls of a container. Both of them are adding the pressure. And Dalton just said, hey, if you want the total pressure of that solution, you add up the pressure caused by each of those things in it. How much do they do? Well, how much is there? The more you have, the more pressure you're going to contribute. So this chi there is the mole fraction. So you're going to have three different types of concentration now you're dealing with. So you're growing up in science. You're going to have three concentration vectors: molarity, mole fraction, and molality. They are all telling you the same thing. How much of something is in something else. Okay, just different ones have different places. In Gen Chem 1, you only dealt with molarity and weight percents, and that was pretty much it. Okay, so there's two more. Don't overthink it. They're just different ways to express concentration of a solute in a solvent. There's something about why the vapor pressure lowers. Let's see, relates this back to boiling point elevation. So you can see from your earlier graph, when you put in a non-volatile solute, it basically does this. It shifts your curve up, and this is explaining to you if you look at these differences. There's the boiling point elevation and the freezing point lowering, and all those phenomena are made because that colligative property shifts this curve that you're familiar with earlier. Okay, another sample problem. Let's see, distillations. Okay, that's pretty straightforward. This is, if you understand this, you understand about anything. You can, this is an aside here, but it basically shows you in a distillation how you're going from gas to liquid and back to gas and back to liquid and back to gas. And each time you vaporize something and condense it and vaporize something and condense it, it gets more and more concentrated in the least volatile solute. And if you do that long enough, you can actually purify something. Hence the term distillation. Okay, here we go. A couple of other sample problems that I've kind of worked out. The whole key, of course, to any chemistry exam is practice, 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 practice. There's another sample problem. Let's see. Osmotic pressure is the fourth kind. The thing I'll point out there is, you know about PV equal nRT, the ideal gas law. Well, guess what? If you arrange PV equal nRT, you get P equal N divided by V RT. Oh my gosh! Colligative property of osmotic pressure in the liquid looks just like the ideal gas law, only they changed the P to a pi symbol. Okay, there's a reason for that, because it basically is acting just like an ideal gas. It's just floating around in a gas of liquid, if you will. Okay, so that should be pretty easy to work with. For those of you nurses and doctor wannabes, this osmotic pressure will kind of sort of explain why when your body chemistry gets off, you can kind of explode some cells, which aren't good for you. Dehydrating or too much fluid or whatever. All right, so they got nifty little names for all that stuff. Okay, check with your local biologist. Right, colligative properties of electrolytes. Let's see what we want to say there. Electrolytes, sodium chloride is going to break into two pieces. That's twice as many ions, so you have to correct the concentration term there. That's what that's all about. Sample problem, colloids. Don't really worry much about the colloid section other than just basically understand what the fundamental colloid is. Wouldn't look for a lot of questions on that. Calculate molecular weight from boiling point or melting point change. I can almost assure you'll have at least one, maybe more, probably on your lab test. It's standard fare to calculate molecular weight from some colligative property. Boiling point elevation, freezing point depression, or osmotic pressure. Bank on it. Okay, finally in our whirlwind tour. And again, I'm just going through these notes and I'm giving you just my initial thoughts on it. Let's see. Kinetics, this is the booger. This is oftentimes viewed as the hardest part of the test, of the course. So basically, here's what we're doing. We're going from reactants to products. A goes to B. And along that path, some of things go slow, some of them go fast, some of them don't go at all. So you need to think about this as either being a downhill ride or an uphill ride. And they always have a barrier to go over. And that's kinetics. It's kind of like Sam Rayburn Dam. See, you've got the water level here and you got your Angelina River way down there. Well, why doesn't it just flood all down there? Because we have this thing called a dam. We've got a raised area here. Now, in chemistry, if this height is real low, a reaction will go much faster than if it's really, really high. And if I could get this energy of activation, this wall, to go all the way up and hit the ceiling, that reaction would hardly go at all. It might even take millions of years to occur. And so that's the idea with kinetics, is how much do you raise or lower this gate so that it occurs? Okay, so what's a chemical reaction? Now let's look at the practical part. How do you do it? A goes to B. Well, this is kind of like the analogy I'm going to give you is that of a sandwich. Yes, 2 breads, 1 slice of meat, 3 pickles goes to 1 sandwich. How many sandwiches? Could I tell you how many sandwiches are being made if I couldn't see the cook? Yep, all I got to do is watch the bread, because I don't need to see any of this other stuff. Every time 2 breads disappear, I know 1 sandwich was made. Or I could watch the stack of meat. I can't see anything else, but hey, every time I see a slice of meat go, what do I know? 2 breads went and 3 pickles went and 1 sandwich. I only have to know one of these to know everything. That's the idea of kinetics. If I look at the rate at which pickles, if 3 pickles are disappearing every minute, what do I know? 1 sandwich is appearing any minute. I've got 1 sandwich per minute. I don't know if I can make a profit on that. Maybe I need to pick up the rate. I'm going to measure the rates at which this stuff disappears, reactants, or appears, products, and then I'm going to judge from that. And these little graphs, like I've shown here in your book, figure 12.2, that's just showing you, see, product, the rate at which one thing increases, and your reactants, the rate at which they decrease. See, some things are increasing that you're making, and some things are decreasing. All right. In this case, sandwich was increasing, and these things were decreasing. Got it? Okay, well, instead of sandwiches in chemistry, we basically deal with chemicals shown here as A, B, C, and D. So a rate of change is how fast A disappears. And A might disappear at a different rate than B. Why? Because I'm only losing 1 meat, but I'm losing 3 pickles. So this is going to be 3 times greater. But wait a minute, that can't be right. I've only got 1 reaction, so I can only have 1 reaction rate. Oh, you're right. So what happens is, if you divide by each of those rates of change for each material, if you divide it by its coefficient, how many of them there are, guess what? You'll get exactly the same value. So if you take the rate of change for each component and you divide it by its coefficient, how many there are, you'll get the same number for every one of these. Does that make sense? Sure, it's the rate of reaction. They're all 1 reaction. You got to have 1 reaction rate. Don't confuse rate of change, rate of reaction. That's what those are all about. So a lot of these questions are just asking you, hey, how fast does this decrease, or how fast does it increase, or at a certain time, how much is left? That's what you're dealing with these equations. Right. 5 factors affecting reaction rates. Those are pretty straightforward and kind of common sense. But basically, the chemical nature, some things are more reactive than others, the physical state. Okay, temperature, the higher the temperature, the faster it's gonna react. The concentration, the more concentrated it is, the faster it's gonna react. Catalyst. Catalyst is, if you have a catalyst that's effective, then it makes the reaction rate go faster. Okay, so you can read through that. With that as an overview, you should be able to kind of understand the concept. Second thing, sometimes this equation here ain't cutting it. We don't have this information, so we can't determine the rate of reaction. Don't know it, can't do it. Can't measure those, don't know. Can't see the sandwiches, can't see nothing. Okay, so there's another way we can do this. Okay, another way we can back into it, and it's called rate laws. And so this is the general rate law expression. Yes, rate is equal to some constant times the concentration of one of your reactants to the x power, concentration of your second reactant to the y power. If you had a third one, it'd be concentration of C to the z power, and so on. A and B represent the reactants X and Y, or some arbitrary superscript called the reaction order. Okay. And so basically, go through this example here. I think it may be in some of those notes that I posted. This is a good one because you do rate of reaction, calculated one way, and then I show you how to do the rate of reaction, calculated another way, and then you can tell what the order is. So that's a pretty good practice problem right there. And then we have some calculations from it. So sometimes this first way I showed you to calculate is what you need, depending on what data you have. And sometimes the rate law expression, RLE, the general rate law expression. Okay, so there we go. So there's all sorts of questions on those. How do you figure out what X and Y is? Oh, you're going to have to use the method of initial rates. So look at those, practice those. It's kind of a little process there that has you just do a bunch of ratios and one at a time, because when you do something like this, what do you have? One equation, 1, 2, 3, 4, 5, 6 unknowns. The data is going to give you 2 of these, 3 of these. It's going to give you rates and concentration of each of those, and you have to use those to figure out what K, X, and Y are. So if you have 1 equation and 3 unknowns, you're going to need at least 3 independent equations, and that's what that's about. Fundamental science. Okay, let's see. Reaction order and rate constants. The key to know is anytime you have a rate for a reaction, the rate has to be a single unit of concentration over a single unit of time. Here I'm using molarity per second. So your K value, rate equal K concentration, your rate equation K unit has got to change. If I have a 0 order reaction, I have no molarity term, and so I need my K value, shown here in these blocks, to be molar units per second. Why? Because the right side has to turn out to be molar units per second. If I have something that's first order and I have a unit of molarity on the right-hand side, now all I need is an S in the bottom. See, I already have an M in the top. So now all I need is an S in the bottom. So now my unit for a first order reaction is going to be 1 over S for K. And finally, I'll take a really goofy one. Let's say I have a fourth order reaction, M to the fourth. Well, how do I turn M to the fourth into an M to the 1 divided by second? Easy. I get rid of 3 of the 4 M's by putting M cubed in the bottom. And I put an S in the bottom because an S shows up. So if you understand dimensional analysis, this is pretty easy stuff. Okay. If don't, you need to work through it. If it's hard, it shouldn't be. Okay, you're not where you need to be with understanding dimensional analysis and how fundamental mathematical operations fit into a course like this. Integrated rate law, sticky wicket. There's the first way I told you to do rate. There's the second way I told you to do rate. Boom. So what happens is the wizards are smart, put these two together, and they did a bunch of algebra and calculus on it, and they came up with 3 equations. Now, the only way they could solve this is they had to take a guess at what X is. So if X equals 1, you get a particular solution. If X is equal 0, you get a particular solution. If X is equal 2, you get a particular solution. So now let me give you a trick of the trade here in Gen Chem. This is called integrated rate law, not general rate law, but integrated rate law. On a test, you're never going to have a rate law that has any more than 1 reactant, because for me to have 2 reactants and for you to do this equation, they get really long and hairy. Like if you have an X and a Y, these things get really ugly. And so those never show up. So one way to tell if you have an integrated rate law is just to look and see that it's only asking you about the concentration of 1 component. If you have 2 or more, it's going to have to be either a general rate law expression or that very first equation that I showed you. Okay. Integrated rate law, you'll see these in a lot, but they can be rearranged to y equal mx plus b, where b is the initial concentration of whatever, of your single reactant that you're dealing with. T is how much time it takes, k is your constant, and this variable right here is the concentration of A at some time other than 0, at some time t. Okay, never mind this. That's from another semester. By the way, you do not have to derive these, and that's what I do. I put that little curlicue there, and it says, and then somebody did a bunch of math or something magical happened. It's kind of like a black box. Well, I did get curious about it. So I asked one of the math professors there at Angelina, hey, man, work that out for me. I want you to take this, and I want you to derive these equations for me. So I gave him a pop quiz, right? So anyway, he said, okay, I'll get back with you. So anyway, so for those of you who are curious, this is his handwriting here. So I said, I want you to work that equation out. Just do one. Just do x equal 1. That's it. Just do one. And he did it. So anyway, so there's his work. So those of you who are going to major in math or something, this is apparently no big deal. He just whooped this thing out in, just a minute or two there. So anyway, but we don't do that because you're lucky. You've got an instructor that I don't do Windows and I try not to do math. Okay, so to at least the derivations of it. I love math equations, but and that derivation stuff sometimes it's not as interesting as it is in a math class. Okay, here we go. So here's what I found out. So this is kind of my little gift to you. So there's 3 main equations that we deal with: integrated rate law expression, and Uranus equation. Yes, and what I noticed is for your integrated rate law, it's got a variable for concentration and time. So normally when it gives you time and asks you concentration, or gives you concentration, asks you time, it's probably going to be an integrated rate law expression, and you're going to use one of those. See, this is cute. Rate law expression. Well, I looked at the rate law expression, and I saw there's a unit of time, and there's a unit of concentration. So if it gives you concentration, ask rate, or gives you rate and ask concentration, it's probably a rate law expression. It's probably going to use that. See, I'm just a good old boy from Jasper making some general observations. See this one right here? See this top one? See, I don't see anything to rate there. There's no rate component there. So I'm figuring if it's asking for a rate, it's probably going to be this one. And then the Uranus equation. Now, you're all supposed to know about the Uranus equation, but notice, if it starts throwing temperature into the mix, well, I looked at all my equations for this chapter, and I only saw one with a temperature, so I think, hey, that's probably it, Okay, so see, there's the temperature. There's the temperature thing, and there's the rate component. And so there we go. So this is not hard and fast rule, but that's just my general rule for when I get one of these really messy questions that throws a whole lot of data. I just look at what it's asking, and if it gives me one of these and asks for the other one, I kind of head that direction first. Okay? So there's some sample problems. This table, I decided to give you on an exam, but I'm not giving you the concentrations of K. So you need to look in the unit folder and get that. Collision theory, this is kind of the theory of why the rates of reactions are what they are, what causes a fast rate, what causes a slow rate. It lets you know what happens with temperature. So that's pretty easy, fair. You should be able to read through that and do it. I've worked a couple of sample problems there. Reaction mechanisms, that's kind of a sticky wicket. Okay, so here we go. So here's the deal with reactions. Not all reactions occur in one line, my dears. Is this A equal B stuff, that doesn't happen that as much as you think. Normally you get like A going to C and C going to D and then D going to B. Well, overall it's A. You're starting with A and you're ending up with B. But what you don't know sometimes is there's a C and a D in the middle. It's a long route. In other words, we're not allowed, in chemistry, we don't drive straight from Lufkin to Diboll a lot of the time. Sorry, the way chemistry works is it's going to route you through Huntington, and then it's going to route you over to Zavala, and then it's going to route you back to Diboll. Okay, so that would be a reaction mechanism where it's not A going to B, Lufkin to Diboll, it's A going to B, Huntington, B going to C, then to Zavala, and C going to B, C going to your final destination, which would be Diboll. Okay, so that's the idea behind a reaction mechanism. Depending on what path you go is going to kind of determine what your rate equation looks like. So what I want to do is show you real quick. Here's the rate equation for A plus B goes to C. All right, so here we go. So there's the general rate law expression. Notice for this, if this equation is true, this means in your slowest step, 1A must have reacted with 1B. But you can have things like this. Maybe in your slow step, remember, this doesn't mean 1A atom and 1B atom, it means 1 mole. So, but maybe in this equation, a bunch of A's hit each other. And then this AA complex, then that reacts with B to give you the final product. Well, in that case, the slow step is going to look like this. It's going to be the point at which 2 A's hit each other. Okay, and so the reaction mechanism is you trying to figure that out. Remember, the rate is governed by whatever the slow step. That's called the rate determining step. That's the prize here. Everything else is fast, so you can ignore it. So the rate of a multi-step mechanism is going to be determined by what's called the rate determining step. And so what the book does is it shows you some ways to find out what the rate determining step is and how to get an expression for those. And then an easier question would be, if I give you a reaction like this, would a particular rate expression represent that or not? There we go. As an aside, the very hardest ones when you have a multi-step ones are when the second or third step is the rate determining. Those get pretty darned hairy to work back. But hey, you should be able to do that. You're a STEM major. Okay, we won't have a lot of those, but you know, at least one's fair game where you have a mechanism and the rate determining step is not the very first step. Okay, and there's what some sample problems might look like. And finally, a catalyst. We know the definition of catalyst, something that speeds up a reaction and isn't itself consumed. Okay, well, what do we mean speed up a reaction? Well, how does that happen? What that means is if you have an uncatalyzed reaction shown by the red, what a catalyst does is it lowers that hump I talked about earlier. And so more water can get over the bridge. Yep, more water can get over the dam and the reservoir. Yes. Okay, and the spillway. And so what that means is a faster reaction rate. And that's basically how the catalytic converters on your car work. Yep, except they use platinum, which is darn near expensive as gold. And that's why your catalytic converter. Some of the catalysts that lower this hump right here, some of them that lower that happen to be what's called precious metals. They're really, really, really expensive. Oh, by the way, why do we have them? Because you have SO2 and SO3 and NO and NO2, and when those formed with hydrogen, they make sulfuric and nitric acids, and that's called acid rain, and we kind of don't like those. And so what happens is this platinum catalyst, it'll take those away. It'll knock those out and convert them to something that's not harmful. Okay. Enzymes talks a little bit about that. Your body runs on enzymes. Enzymes basically are nature's catalyst. That's the punchline here. Okay, so we call them catalysts in chemistry when it's in your body and it's a natural product. Your biologist is going to call that in situ catalyst. They will call those enzymes. And for example, the conversion of CO2 and water and carbonic acid is slow, but if you put it in the presence of carbonic anhydrase, that's an enzyme. The rate will increase to more than 1 million conversions per second. Let me get this straight. You're going from 0 miles an hour to 1 million miles an hour. Okay, no, not even 1 million miles an hour, 1 million miles per second. From 0 to 1 million miles per second. That's a big change. That's how much lowering this peak right here, this energy of activation, how big of a difference it can make. And that's kind of sort of what this chapter is about. And then it puts a bunch of math to this stuff. Yes, where you kind of figure out, you plug numbers into it. Okay, so you've got those equations. So there is a lot of math here. It's simple math. It's plug and chug. The hard part is not so much the math. That's pretty straightforward. The hard part, of course, is knowing what math to use. And with that, let me see, equilibrium's the next chapter. And so with that, this is a horrendously fast, granted pseudo-sloppy overview, just my initial thoughts of what I see when I run through those notes. That's it. Bye now.